All right, so we've been looking at the precise definition of a limit, and just to review, remember that if we say that the limit as x approaches a of f of x equals L, that means that for every possible epsilon greater than 0, no matter what it is, we can always find a corresponding number delta greater than 0, such that, okay, if x is within delta units of a, okay, because that's what x is approaching. So as long as it's within delta units of a, then L will be within epsilon units. Okay, the limit will be within epsilon units of the function f of x. All right, so that's our definition. So let's use that once again to prove that the limit as x approaches 3 of x squared is 9. Now, if you look at it, you're probably thinking, yeah, it's totally obvious, but can you prove it? That's the question. Okay, so if we want to prove it, it has to match this definition. So we need to show that for every epsilon greater than 0, there is a delta greater than 0, such that the following is true. If x, now a is 3 in this case, so x minus 3, the difference between x and 3, is less than that delta that we're going to find, then the difference between the function, which in this case is x squared, and the limit, which we're trying to show is 9, okay, will always be, okay, so it'll always be within epsilon, whatever epsilon we happen to have chosen. Okay, so remember, this is kind of a two-step process. So step 1 is to choose an appropriate delta. And as you recall, delta is going to be related, okay, to epsilon in some way. So we're going to want to start here with x squared minus 9 being less than epsilon. Okay. And we'd like to do some work on this and see if we can get it down to a point where we can deduce something about x minus 3. Okay, so this one is a little bit trickier, so you gotta put on your thinking cap to follow this one. Okay, well, hopefully you look and say, well, how is this related to x minus 3? Well, x minus 3 is definitely a factor. Like, I could factor this into x plus 3 and x minus 3. Okay, so I at least have that x minus 3 part of it. Now, I can't really just pull this x plus 3 out. That's a variable. I can't say something like, oh, it's always positive, or I don't even know what x is, so I can't pull it outside of the square roots. I mean, of the absolute value bars. Okay, but I can do some just logical reasoning about it. Okay, so I'd say, all right, well, if I think about this x plus 3, okay, if x is approaching 3, and I want x to be near 3, what does it actually mean for x to be near 3? Okay, well, you know, here's 3, and I'm probably talking about something small. So if I go out to, you know, 4 or down to 2, so within 1, you know, plus 1 or minus 1, that's a pretty reasonable window there. I'm probably expecting some tolerance like much smaller. I'm expecting to be closer than that, probably to 3. Okay, but let's just say I'm within 1. So let's say, okay, so let's suppose that x minus 3, or well, let's write it this way. Let's say that x is between 2 and 4, like this. Okay, I could write it. It's x minus 3, absolute value is less than 1. I'm just going to end it with that anyways. I'll just go ahead and write it that way. If you wanted to start there, so you could say, all right, I'm within, 1 unit. So I could do something like that. It's just going to turn into this though. All right, so let's say that x is between 2 and 4. Okay, well, if x was between 2 and 4, then if I add 3 here, and add 3 here, and add 3 here, then that would put x plus 3 between 5 and 7. Okay. And so that means, like, the biggest thing that I ever expect x plus 3 to be would be 7. Okay. So this, if I replace this with 7, and that's the biggest thing I can ever get x reasonably expect it to be, and still force that to be less than epsilon, I'd still be okay. Okay. So I've got that. Okay. And so now 7 is always a positive. I can take that out. And so that would give me x minus 3 is less than epsilon over 7. Okay. Now, the tricky thing about this is I've sort of put two conditions on. Now, I assumed here that the absolute value of x minus 3 had to be less than, I actually probably should have just put a less than, not equal to. I don't want an equal in there. Okay, so I have two things. So I chose that, I just assumed that x minus 3 was less than 1, and then later on I chose down here x minus 3 is less than epsilon over 7. Okay, so I really have to choose my delta carefully because like I have these two different conditions. So what I'm going to have to do is take delta and choose it so that it's the minimum of 1 and epsilon over 7, whichever is smaller. Okay. So I don't know which one it is, but this makes it general. So any conditions that I've put, these ones that I introduced up here, to make this work out, both of them are met. So this condition and this condition are both going to have to be met. Okay. So I've chosen my delta to be the smallest of those two, because if it's only this one, then if that condition isn't met, then I can't guarantee it for every epsilon. I can only guarantee it when x is between 2 and 4, right? What if it's not between 2 and 4? Well, then I have this to fall back on. So now this can generalize it for every single value of epsilon, not just the ones that are going to be in this range. All right. So step 2 is to show that it works. Okay, so we're going to say let delta be the minimum of 1 and epsilon over 7. Okay, so that means that if we've got 0 is less than x minus 3 is less than delta, okay, then what's going to happen? All right, well here, since it's less than delta, we know two things. We know that x minus 3 is less than 1, and we know that the absolute value of x minus 3 is less than epsilon over 7. Okay, so it's the minimum of those two things, so it has to be less than both of those things. Okay, so let's follow both of those paths, I guess, somewhat. So if we have that the absolute value of x minus 3 is less than 1, Okay, then this gives us two things. We have x minus 3 is less than 1, okay, and x minus 3 is greater than negative 1. That's how you solve an absolute value inequality, right? So this would give us that x is less than 4, and this would give us that x is greater than 2. And that's no surprise because that's what we had over here, right? Okay. And so, of course, we have x is between 2 and 4. And so if we add 3 to both of these, or to all of these, then we have x plus 3 is between 5 and 7. Okay. And so now we have x plus 3 is less than 7, and the absolute value of x minus 3 is less than epsilon over 7. Okay, so if I take this number that's less than 7 and multiply it by this number that's less than epsilon 7, then I'll have that x plus 3, and I can do even the absolute value of that, okay, times the absolute value of x minus 3 is going to be less than, well, this one is less than 7, and this one is less than epsilon minus 7, so this product has to be less than that product. Okay, and so this would give me the absolute value of x squared minus 9 has to be less than epsilon. Okay, which is exactly what we wanted to show up here. Okay, so by definition, the limit as x approaches 3 of x squared is indeed 9. Because I was able to show that no matter what epsilon you choose, if I let my delta be the minimum of 1 and epsilon over 7, I can guarantee that the absolute value of x squared minus 9 is less than epsilon. Okay. Now this was definitely a trickier proof than the ones that we did last time because we had to do a little bit of guesswork. So I would, hang on to this idea if you have to factor something, okay, and one of the factors is what you're looking for, then reason about the other factor. But just remember, all the conditions that you put on have to be taken into account when you choose your delta. You can't just choose epsilon over 7. You have to choose the minimum of 1 and epsilon over 7 because of the two conditions that we put on it. Okay, so this is one that you might have to go over a couple of times and just convince yourself of it. Try to recreate the proof yourself without watching it and just see how you do, because this one's a little bit trickier. All right, the last thing we want to look at is an infinite limit, so limits that go to infinity and eventually to negative infinity. Okay, so you'll notice that it's slightly different because there is no epsilon in this definition. So let f be a function defined on an open interval that contains the number a, except it might not be defined at a itself. Then the limit as x approaches a of f of x is infinity means that for every positive number m, okay, there's a positive number delta such that, okay, so once again, if I'm within delta, if x is within delta of a, we can guarantee that f of x is larger than m. Okay, so sort of graphically, here's my m, it's some kind of maximum, okay, or some large number. And so as long as I'm within delta units of a, my value, I know it's going to be bigger than that. Or this is, I guess, actually sort of a minimum. So this is a boundary here. Okay, I know that f of x has to be bigger than that. And so notice, if I move this up, if I take and I go, oh, well, I'm going to make m even bigger, and I move it up here, well, now I've got to be even closer than I was before. So once again, as I move m up and make it bigger, I'm going to have to move delta closer to a. So I have a smaller window that can guarantee f of x is always bigger than m. So as I move this up, I'm going to have to move these in and get closer and closer and closer to a and approach a from both sides. Okay. So once again, let's use this definition to do a proof. Let me see if I can get this all on the screen at the same time. Okay. All right, so we want to prove that the limit as x approaches 0 of 1 over x squared is infinity. Okay, so what we want to do is go to the definition. So this is what I'm trying to prove here. So that means we need to show that for every m, positive m, there is a delta, a positive delta, such that if, okay, and in this case our a value is 0, so x minus 0 less than whatever that delta is, then f of x, in this case it's 1 over x squared, has to be greater than m. Okay, so I've just taken from my specific problem, okay, and substituted in 0 for a, and I've substituted in 1 over x squared for f of x. Everything else in the definition is the same. Okay. All right, so we know that wherever that m is, delta is influenced by that, right? If I move m up, delta has to be smaller. If I were to move m down, it can get larger, but they're connected. All right, so I'm going to start with my 1 over x squared has to be greater than m, and see if I can figure out what delta I'm going to have to choose from that. Okay, so x squared is a positive number, so if I multiply both sides by x squared, I would get mx squared, and then if I divide both sides by m, I'll get 1 over m over here. Okay, everything is positive. I don't need to change the direction of that at all, so I have that 1 over m is greater than x squared. Okay, and now I just want x by itself, so if I take the square root of both sides, the square root of x squared would be less than the square root of 1 over m. And so 1 over the square root of m, okay, would be greater than x. So if you look at that, I just want x to be less than delta. How should I choose delta? Well, I'm going to choose delta to be 1 over the square root of m. I'm not going to bother rationalizing it. I'll just leave it like that. Okay. So that was our first step, was to choose wisely. Okay, so now I've chosen, and step 2 is to show that it works. Okay, so we need to show that for any m, positive value of m, okay, okay, I'm just going to do for any m, all right, we're just going to do let delta equal 1 over the square root of m. Okay. Then if we have this, then what's true? So we just have to follow this down and hope that we get to here. Okay, well, oops, this is supposed to be like that. All right, that means we've got the absolute value of x minus 0 is less than 1 over the square root of m. All right, so If we square both sides, well, if we square the absolute value of x, we're going to get x squared. And if we square this side, we'll get 1 over m. Okay, and then again, if I just multiply both sides by m, I would get m times x squared, and then divide by x squared. I'll be left with an m over here, and I'll have 1 over x squared on this side. Okay, and if I'll just rewrite this so it looks like that. Okay. So I did show that if I started with x minus 0 is less than delta, okay, then I do indeed get that 1 over x squared is greater than m. Okay, so by definition, the limit as x approaches 0 of 1 over x squared is indeed infinity. All right. So as you can guess, there's going to be a similar definition for negative infinity. We're actually not going to work out a problem from here, but I think you can see that it would just follow the same kinds of trends. So here we have a function defined at an open interval that contains a. It might not be defined at a itself. The limit is negative infinity if for every negative number n, there's a positive delta, so that if you're within delta, if x is within delta of a, then the value of the function is less than this negative number n. Okay, so the picture just kind of changes. So here I've got a negative value of n. Okay, I'm within delta, it's hard to see, of a, and as long as I'm within that bound, I'm going to get my f of x value that's less than that negative number. Okay, and then once again, notice if I take this n and I make it a smaller number and I go out here and n is out here, well, that's going to really affect what's going to happen with delta. It's going to have to be even smaller. I'm going to have to be within a smaller range to get my value up there. So the n and the delta are intimately connected, just like the m and the delta are just like the epsilon and the delta were in the regular limit proofs. Okay. All right. So yeah, section 2.4 probably has the information that's hurts your brain the most, and you're going to have to think about it and read through it and spend a lot of time on these things probably, but it's probably one of the most difficult things to comprehend. So if you don't get it the first time, you might watch it again, read it in your book, try some proofs, and just work through it until you can convince yourself that the definition of a limit really does precisely define what we've been talking about in terms of limits so far.